Delbert Larson, welcome to the show.
Thanks for having me on today.
Yeah, no, it's a pleasure. I want to do a lot more content about the nature of reality, cosmology, physics, and it was very interesting. We just randomly came across each other on a thread, and I looked into your background, and it seems like you have a very, very interesting background, and maybe some theories that are in opposition to conventional physics, if that's such a thing, or at least the physics establishment. So that's interesting space for me. So for those of my listeners who aren't aware of who you are, what you do, what your background is, would you give a quick bio?
Sure, I'd be happy to do that. I got a PhD from the University of Wisconsin in accelerator physics many years ago now, and my PhD thesis was based upon electron cooling of antiprotons for the Fermilab accelerator complex. I designed and then subsequently led the building of a 3 million volt, tenth of an ampere intensity electron beam system. The relevant thing there is that it did work. It worked according to the design, and that used what is known as relativistic calculations in that design. From there, I spent some time at various national labs and universities. I ended up at the superconducting supercollider south of Dallas for a while until that project met its demise. I was doing longitudinal dynamics for the design of that device. Following that device, I got another opportunity to actually build an accelerator. So I designed and built what was called the Fermilab PET accelerator. It involved beams of about 1 million electron volts of energy, so that was non-relativistic, but it also worked according to its design. After that project ended, I was looking around for further work in the physics community, but I ran into a situation where almost nothing was being built. There was a lot of design work being done, but there weren't any plans. Once the superconducting supercollider went under, the high energy physics community took a pretty big hit. And I had work that I wanted to do in two areas. One was colliding beam fusion for energy production. And the second one was I had some ideas as to why, or that I had some ideas that opposed the relativistic viewpoint that is taken by mainstream science. And so I spent time on those areas on my own while earning a living in IT to support my family. So that's kind of the background of my career.
Got it. Got it. Thanks. You initially got into this field, or at least were attracted to it, because you thought oil was running out, right? Like that, or that was the concern. And so you're looking at different ways of generating energy, right?
Yes, that's correct. Back when I was in high school, there was a fear that by the year 2000, the oil would dry up, and that would have been a horrific thing. And so I wanted to focus on looking at an alternative energy source, and fusion is a tremendously positive. It has a tremendously positive potential if we can harness it. That's the interaction that fuels the stars, and of course our sun's one of those stars. And the energy that you can get out of fusion is about 20 million times more than you get out of chemical reactions, and then you get your fuel back essentially, because the fuel is found in tremendous quantities in seawater. It's the deuterium in the seawater, and only a certain percentage of that is the deuterium, and so it's a very tremendous source of energy that we should try to harness in the future. And so I did some work in that regard.
Got it.
Unfunded
Got
so
it.
far. Yeah.
Of course, of course. We could probably
Yeah.
go into reasons for that, but I
Yeah.
digress. I'm really interested in heterodox thinkers, right? People that bring an alternate view to the mainstream. And so that was really attractive for me. And I think there's this schism, might not be the right word, but there's this debate in the physics community, primarily, I think, spearheaded now by Eric Weinstein. He's really, at least from a media perspective, he's really challenging the Leonard Suskins, the string theorists, Michio Kaku, and the establishment, the intellectual establishment that has sort of hijacked physics for a long time. And I think this is a interesting time where the door is open to new ideas and new theories that have been sort of suppressed by the mainstream, the sort of intelligentsia, the ivory tower, keepers of the orthodoxy. And so that's why I wanted to talk to you today, man. So, and apologies if this isn't possible. Like I said, I told you when we were talking offline, I'm kind of a dum dum, but I'm curious. I'm really interested in the subject. Is there a way that you can explain your theory, which I believe is a reboot of the prior ether theory, maybe a modernization and an improvement upon it, talking about quantizing space and all sorts of things that frankly I don't fully understand. Could you speak to that in a way that maybe a regular person could understand?
I think that would be a tremendously good challenge to undertake. So we can begin. And and so the ether is not space. First up, the ether is a substance which would occupy all of space. So
Mm.
that's a separate thing. And also in the theory that I have, and really the one that even was around earlier, the theory is that the ether is a solid. So you can think of essentially one way to think of it might be a giant block of ice that would go from here to the furthest galaxy. Now it's not ice because it's a different substance, but it is a solid and it occupies that entire region. The reason it needs to be a solid is it's known that light is transversely polarized. And what those words mean is that the oscillation is going in one direction that's perpendicular to the direction it's traveling.
Hmm.
And if you think of a wave on a string, if you snap a whip, you get a transversely polarized wave, and that whip is a solid. And you can also get waves in other solids as well. So that was the first observation, and it wasn't mine by any means. It was known probably maybe 100 years, maybe more, prior to my birth even. So it starts there. And then from that simple proposal, I went on to, well, I guess maybe we should do a little bit of a backdrop too, because as to the reason why the ether was abandoned um, over 100 years ago. And there was an experiment done by Michelson and Morley that's quite famous. And if you go online, and even in some physics textbooks now, it will say that the Michelson-Morley theory disproved the ether theory. But that's not actually accurate because what it did was it didn't find the Earth's motion through the ether. So there was this back in the 1880s, there was a view that there was this ether that supported these transverse waves. And so Michelson and Morley set up some mirrors. They were at right angles to each other, and the light would go on one arm and it would go on the other. And if the apparatus is moving through space, then one path would go like this. I can't get it all the camera there, and the other one will overshoot and come back. And if you calculate the math, you might be able to align them both so they all come back at the same place. But then when you rotate it, you're going to get a change in the distance traveled relative to the two arms. And so the expectation was that if you looked at the interference pattern that was created by the light bouncing back and forth, as you moved it, you would be able to see the interference pattern move, and the mathematical calculations then led to an expectation of how big that would be depending on how fast the Earth was moving through this ether. And when the experiment was done, they found none. So that shook the groundwork of what people were thinking about at that time. But there was a man named Fitzgerald, and there was another man named Lorentz, who
Hmm.
came up with the observation that if the apparatus is moving right to left for me, and if the right to left arm shrinks by just the right amount, then as you rotate it, so that the other one's now shrunk, that you would indeed see no change in the fringe pattern. And that phenomenon was called a length contraction. So that was proposed still within the ether. There were other experiments that were done later. Troughton Noble was one, and there were several others that indicated that in addition to a length contraction, it was also determined that there must be some sort of a time dilation, that clocks as they move through the ether would run slowly.
Hmm.
So that was where things stood as of about 1905. Lorentz had written down the equations for both the time dilation and the length contraction in a series of equations called the Lorentz transformation equations. But in his interpretation at that time, the equations related the what he would call the fictitious coordinates that one would have based on the fact that their clocks are running slow and their meter sticks are shrunk. So if you were to set up a coordinate system with those faulty instruments, you'd come up with some x, y, z, and t. And then if you would compare it to the true time and lengths that would be observed in a frame at rest with respect to the ether, you'd get these transformations. So that's where things stood, but there was a lot of grumbling about the fact that we really shouldn't be introducing into fundamental physics something so radical that just as the result of some specific experiments. And the complaint was that every time we get a new experimental result, we're going to throw something into the mix. So there should be some sort of underlying principle or something we're missing. There was a thought that we're missing something. And it was known at that time that a result of the Lorentz transformation equations were that no matter which one of these faulty frames you would go into, they're called a frame. When you go from one set of space-time coordinates to another, each individual one is called a frame. And when you would go from one frame into another, the speed of light would always be the same, which was kind of an odd result. But that's what came out. And I believe it was Poincaré suggested that there might be some sort of a relativity thing going on. But it was Einstein who deserved the credit, because what he did was he raised the speed of light to a postulate. He said that this was sort of a foundational pillar of nature. And then he essentially ran the derivation backwards from there and derived the Lorentz equations in a very elegant way. And so that then managed to set aside this need to put it in the Lorentz contraction and the time dilation in, putting them in an ad hoc way, and instead deriving them from some first principles, but at a rather significant cost, in that prior to relativity, the time and space were considered to be the primitive quantities. And then you would basically, space would be the stage upon which physical events occur, and time would be the order that they occur in. And what happened with Einstein's work was that it messed those things up, because what would happen would be if you have a length in one frame and then you've got a moving observer in another frame, a length is a series of two events, one on each end of the stick. Well, when you start moving with respect to it, you introduce a time difference on the ends of your stick. So it makes time transform into space and space transform into time, depending on how the observers move. So it came at a cost, and it wasn't really embraced that much at that time. But then Einstein went on over the course of the next 10 years to develop his general theory of relativity, which at the time it answered which is a very bizarre idea, because it uses a space-time continuum, and Minkowski deserves some credit for that as well, where the variables of time and space do interchange with each other as they do in special relativity. But in addition to that, mass can curve that space-time continuum. And the reason that was so important was there was an unknown problem there was an unknown solution to a problem of Mercury's orbit that at the time no one could understand why the orbit was shifting in the way it was. And general relativity came in and it solved that problem. It correctly calculated the orbit of Mercury. And then subsequent to that, it also calculated the bending of starlight in a test. And those tests were then heralded as more or less proof that the relativistic approach was correct. So that's kind of the background to it all. But as can be seen here, or inferred maybe, the uh, the ether itself really hadn't been disproven. It had just been moved. We've moved beyond it for uh, some fairly sound reasons. But
Sorry,
beyond
real quick, real
beyond
quick. Is it because general relativity was so functional? Is that why they moved beyond it? Because it sort of worked with respect to predicting, various things. I mean,
yes,
we rely on general relativity a lot, and that doesn't necessarily mean it exactly describes objective reality, but it's useful enough. It kind of seems like a good reason to sort of generally accept it.
yes, yes. It agrees with all observational tests that are done against it, and that's a very good reason in science, and that's the goal, of course, is you want to have a theory that agrees with everything. But the thing that still hangs out there is just because a theory does agree with everything doesn't mean it's the only one that will. And so there's still room for an alternative, and the appealing nature of the explanation for the transverse oscillations of light still hold if you go back to the ether. But the bigger problem is that relativity and quantum mechanics are incompatible. That's one big problem. And the second big problem, in my view, a lot of other people don't necessarily share this, but in my view, and although I've been hearing more that do, is that there are inherent infinities associated with general relativity, in that this concept of a black hole is called a singularity. And that's because all of the matter ends up going to a point, not a very small region, but a point. And whenever you introduce, in my view, whenever you introduce infinities into physics, it's essentially just the rug we sweep everything, all of the unknowns under. You're still missing. You're probably not correct. So relativity's got those two big hurdles, and the confrontation with quantum mechanics was brought up by Einstein himself.
This is
He
the
threw
entanglement problem, right? Like this is the quantum entanglement.
yes, yes, yes. Well, it's that, and although it even occurs really in something as simple as the two slit experiment, because there's an experiment called the two slit experiment
Mhm.
where a light will impinge upon two slits, and then you see an interference pattern on a secondary wall further downstream. And there's still the question about, well, okay, we've got, if you turn the knob down enough, right, you get one speck at a time. And if you get one of the specks at the extreme edge of that at that interference pattern, that then means that you can't get another speck anywhere else on the wall. And if the distance is far enough away and the time that it took the photon to interact at the wall is short enough, then you can run into a problem there too with relativity, because relativity messes up what's before and what's after when you're at a finite distance.
Oh,
So it's more than just the entanglement problem, but the entanglement problem kind of has the I guess the sex appeal about the whole thing, because everybody, well, there was these predictions made, and then John Bell did a tremendous amount of excellent work on setting up a test to see if quantum mechanics was giving us the right answers. And then those tests were done, I think it was in the 80s, by Aspect et al. And they came out in support of quantum mechanics. And that was where it was entangled, because those experiments take a state that decays in a known way, such that two particles are heading off in different directions, but their total spin must must satisfy some constant. And so when you measure one, then you imply information on the other. And there again, you have a situation where, again, relativity does not handle that well, because once you've got a physical separation, then you no longer know what it means to be what's before and what's after. And so all of this goes back to, for the longest time, certainly throughout all my education, it was known that relativity, nothing could go faster than the speed of light. People have been arguing against that lately, but every time I've took a deep dive into any of these, it's being hid by another realm of infinities. The favorite one was the many worlds hypothesis, where every time there was a quantum reaction, an entirely new universe comes into being. But most of the alternate explanations accept a version of that. It's not obvious, or they define it away. I mean, one of the latest ones is this theory that we're in a simulation. But the
Yeah.
thing about that is that, okay, if we are, there's still a reality to the simulator, and you haven't answered the question, and it's this continual series of dodges. Whereas if you go back to an ether theory, time is the primitive, space is the primitive, absolute simultaneity is reestablished, and therefore, if an event occurs at the one end of that two-slit interference pattern, we know that the concept of before now rigorously does apply, the before and after concepts. And so it becomes clear as to how that's happening. And you can also do the same thing with all of these quantum tests, the entanglement tests. And there's one that came out not that many years ago called the quantum eraser, where they called it a delayed choice experiment. And under the proper set of rules for how wave functions occur, you can understand that as well. The problem comes in with relativity not having a well-defined concept of simultaneity and before and after. So those are the issues there. And then when you couple that with having the infinities that relativity has, there's kind of two strikes against it. Because the other thing is, not only does relativity have this singularity that's known as the black hole, but it also has singularities in the sense that it is manifestly a point-like theory of events in a curved four-dimensional space-time. It has to be point-like, because otherwise you run into problems again with simultaneity issues. If an event has a finite size, not non-zero, then what's happening on one end needs to communicate to the other end, just like that two-slit experiment needed to do, only on a much smaller scale. And so it has those two issues. That it's led a lot of physicists to near insanity trying to understand, because relativity explains so many things so beautifully and so simply that it was it was the thing that wasn't questioned, because it seemed that quantum mechanics was. And a part of the problem there is that quantum mechanics is inherently non-determinate. There's the role of chance in there. And physicists tend not to like that. When a physicist sets out to go understand the world, they're not looking to say that, well, F might equal ma, but maybe it equals F equals ma plus a delta A. And that's just not something that's desired. But quantum mechanics does that. Quantum mechanics tells us that there's a spread of answers that we're going to have to live with. And so quantum mechanics has been the one that's had the arrows pointed at it instead of relativity in that confrontation. So that's where we were, or where we are. And so I went down the path. So now that's all the background. And so I went down the path of starting again with that solid ether. And I fairly quickly realized there needed to be two parts to it. So you've got a plus ether and you've got a minus ether. And they exist, they're two independent solids that overlap each other that extend from here out to the galaxies far beyond us. And then I added the possibility that, well, what happens if some of it gets knocked out? So if you have enough energy, like, I don't know, a gamma ray, say, and it collides in just the right way with maybe another gamma ray, and you deposit a lot of energy into the ether, you can knock out small pieces of the ether. So you knock out a plus piece and you knock out a minus piece. And what'll happen is if you've got some extra ether in there, it's going to push the light kind ether away. It's like putting a water balloon inside your bathtub. It's going to radially push everything out. And that radially pushing out of that light kind leads you directly to an equation called Poisson's equation, which is a fundamental equation of Maxwell's equations. Now, there's a detail that not only does this water balloon push the light kind water out, but there's the anti-water and it pushes a little of it in, and that's worked out in detail in the paper. And that's the physical thing that happens in that effect. And then there's also a few other things. The earlier ether was just known to be a solid. Well, we've come a long way since then, and with our understanding of quantum mechanics, and we generally believe that physics at the atomic scale is a quantum phenomenon. And so I assumed that the ether itself is quantized. So it's atomic and quantized. And so you have a fundamental quantum of the ether. And so if it's quantized, then you're going to have a situation where neighboring quanta are going to form a cube around it. So you're going to have neighbors on all sides. They're going to push each other by what's called the Fermi exclusion rule. So you basically have it sitting inside of a square well, 3 dimensions. And there's a mathematical, it's very straightforward. It's in undergraduate physics courses of the pressure that you're going to get on the walls of that cube then. So there's going to be a quantum pressure pushing outward. And then I postulated also that the ether had to be under tension because these transverse waves we talked about on a whip, there's also, or if you did it on a guitar string, you get waves. There's a tension there that also plays a role. So if you slap a tension on the ether and then you've got this quantum effect, you can find the equilibrium of what that cube is. So those are important parts of the analysis. And then I think the last piece is if this moving piece that I told you did the moving up, if it flows through the ether, the flow itself will also generate forces. And then after after some, it's rigorous mathematics, but it's not at the, I mean, it's at the level that a senior in college physics courses would be comfortable with. You then can fairly straightforwardly derive Maxwell's equations. And furthermore, you can also derive the Lorentz force equation. Now, the Lorentz force equation is the equation on charged particles due to electric and magnetic fields. And so all of this, so these very simple ideas of this quantized cube thing, under tension, motion, repulsion, that gives you both Maxwell and the Lorentz force equation. So that was all kind of cool. And then the last piece to the puzzle was what happens when you've got mass. And so that was of all of the present postulates that go into this, that one's a little bit quirky because the postulate is that mass will affect the tension and the quantum fields, and that's not that quirky, but it's the way it does it because it affects the tension more and the quantum less for one type of ether, and for the other type of ether, it's flipped. But once you make that assumption, then you can again go through all the rigorous derivations, and you get Newtonian gravity at the lowest limit, and then higher up you start to get secondary effects. And One of the secondary effects turned out that it pretty much exactly matched the calculation of Mercury again. So that came out, and then the other the other term is a 1 over r term in gravity that's fairly small, but by the time you get to galactic scales, it's large, and it maps pretty much identically to what is now known as dark matter.
Hmm.
So so all of the pieces kind of fit together very, very nicely, and that's pretty much where things are now. It does also provide some answers to some questions that were for a long time open in cosmology, which is where does the energy come from a supernova? Lately, I've heard that there's some theory that neutrinos are providing it, but I really don't understand how that works because neutrinos generally don't interact very strongly with matter, so I'm not sure how they're pushing all this stuff out. But people have looked at it, so and they're bright people, so it's just easily could be that I just don't understand it. But in the theory that I have, uh, this same this same of gravitational effect that affects the planetary motions it's a negative field. I call it a negative field mass. And so if you were to take a star and you crunch it down into a neutron star, which is what happens in these supernovas, the you're going to have a lot more negative mass when you're done. And that's going to, by E equals mc squared, you've now liberated a lot of energy. And so it explains that. And by the same token, it also explains the tremendous power of quasars. So, because quasars could simply be the formation of the large central objects. Now, the ether theory doesn't have a black hole, but it still will have very massive central objects. They could be at neutron star densities. They could be something entirely exotic because once you start getting into millions and millions of solar masses and you've got those sorts of pressures, it's really hard to nail that down, and it would be very hard to get any experiments done there. But so something's there, and it would have a lot of this negative field mass. So what we might be seeing is the formation from clouds of gas and dust and other stars and stuff like that into these large central objects in these distant galaxies. So I find it all quite appealing from a common sense standpoint, the whole thing, because it also brings us back to the primitiveness of time and space. I mean, when you were born, you were a little kid, you knew what time it was. Physicists no longer know what time it is. So you have to, you go back to that concept of time. You kind of knew what time was, and same with space. And to think that they're the same thing is it's quite revolutionary. I mean, Kant played with that idea, and Einstein embraced it. But this ether theory goes back to the rather, I would say, more obvious situation. Now, just because it's obvious doesn't mean it's correct. I
Hmm.
agree, but just because it's obvious also doesn't mean it's wrong. So that's where we're at with that. I don't know if that was clear enough, or if there's things that could probably be improved upon.
Well, it was relatively clear to me, but as you spoke, it just kept. I have questions that kept bubbling every other sentence, and so
Oh,
I'm going to try. I'm going to try to grasp at some of those that came up.
okay.
So quick question: how long has this theory of yours been in existence, and have you submitted it for peer review yet?
I worked on, well, first I published a paper on Maxwell's equations being derived from the two-component ether back when I was the dying days of the supercolliders. That's almost 25, 30 years ago. The more recent version I started about 8 years ago. I finished about a year ago or a little more, and I published it in the peer-reviewed journal Physics Essays. Physics Essays is devoted to looking into ideas that are outside of the mainstream. I was unable to get even a review at the physical review. They were kind enough to just say that we don't take this paper. And then as you go down the pecking order, they get more and more shrill about how their quality is too high for you. But that's just what you face. But Physics Essays does send it out for review. It has been reviewed. I would welcome more review because the math, again, it's straightforward. It's just, unfortunately, it's long. I mean, it's kind of a long work to work through, but that's where it's at, and that's how. Yeah.
Very cool. And I was going to ask, like, based on that review, or based off what you're hearing, it doesn't have to be a formal review. What are the arguments against your theory? Like, what are the most common arguments that you run into?
Well, on X, I've been getting some arguments. I would say more than half the time, well, probably even maybe 80%, it's somebody's got their own contra theory. And I'll take time with it, and I will normally find uh, fairly early on in their work an inconsistency with notation or mathematical errors, or it's stuff like that. I've also gotten some. There's one gentleman for sure. He keeps coming back with things, but I've mentioned to him that he's bringing up ideas that. Well, here's one. Uh, right now, it is believed that space is expanding. That's came about last, because again, when I was in grad school, that was not the case. But I point out that all of this is hinges on a thing called standard candles, and the way that whole idea came about was, okay, you've got these supernovas that are known to put out so much energy, and then we assume it's always going to be the same. Well, if it's not always the same, then we really don't know that, because the expansion is it's largely occurring at very, very distant objects. And also within an ether theory, I mean, it's not entirely certain that the ether is going to be the same density from here all the way out to 100, 100 billion light years away. So, so if you go back, so part of it's that. The bigger problem I have with regard to the standard journals is, well, the editor at Physics Essays mentioned back, he says, well, they don't take it because they don't have anybody who's an expert in the field. So, the harder part is it goes back to those 80% that I've got, because it's more than that. There's a cottage industry in coming up with new ideas, and they're all wrong. And
As most are.
most of the time they're wrong. They're ludicrously wrong, and so nobody wants to take the time. And I saw this thing on X2. It was something. It was it's now a meme that the first thing they say is, "Oh, I've got this perpetual motion machine," and they go, "Oh, no, you can't. It violates this." Well, show me a mistake in my math, and they leave it at that. And I'm thinking, you should find the mistake in their math. It's probably going to be pretty trivial to do. It should only take you 10, maybe 20 minutes to find the mistake in the math. Go ahead and find it. And then if you don't find it, well, maybe they're on to something. But the thing is, they're largely not going to be. So people don't really want to take a lot of time. And then it's very difficult to, because of the career path I took, which was, I left the field to go do this, because the other thing was, when you're at the larger institutions, there's a lot of pressure to conform to the norm. Uh, I tried to publish a paper at the SSC on, uh, it was on special relativity, and I sent it into the physical review, and they were fine with that. And then it came back, and the reviewer said that everybody knows that special relativity does not contain a length contraction, and I was aghast because it's not true. And so then I sent it back to them again, and I said, well, I wanted it to be adjudicated, and so they sent it back to the higher up editor, and he sided with the original reviewer. This is nuts. So I went back to the SSC and I said, okay, now I'm going to submit it to this other one, and they then set up a publications committee to review publications before they could be sent out for review, because the thing is, there's there's a lot of like crazy ideas, and you don't want to be wasting the taxpayer money supporting somebody, all of that stuff. And so, and especially at big research universities, they've got so many funds coming through that they're paranoid about, you've got to get it right, and unfortunately for science, if you're going to go ahead, you don't get it right. I mean, you make a whole bunch of mistakes, and then you find out what went wrong, and then you try to tweak it, and it takes a lot of time. And then that's that's one way to advance. The other way to advance is the way we're doing it now, which does also work. They call it raging incrementalism, where you start with these things that you know, and then you slowly, go forward. But you're never going to hit the fundamental problems by looking at it that way. So the biggest hurdle at the moment is trying to get serious review, because it's entirely possible I've got an error. I don't think I do. I would certainly, the first thing I would be is mad, and then I'd have to like lick my wounds for a while and thank the person that found the error, but then return to it, because so many things have come that work out so nicely, and some of them I wasn't expecting to happen. That I think there's a thread of truth here, but the big battle now is to get some visibility, and I thank you for this. This is the second podcast, and we'll see how it goes, and that's where things are right now.
Great. I would recommend reaching out to Eric Weinstein. I know he's a huge accountant and maybe won't respond, but he seems to be very open to this, heterodoxy in physics right now. He's leading the charge against the string theorists and the keepers of the orthodoxy. So I don't know, Eric, if you're out there, give him a shout out. I wanted to ask a couple of questions. Or so actually, you can respond to that real quick if you want to. I got some tons of follow ups.
Okay, no, I just wrote his name down because make sure I follow up with him. So thanks.
Perfect. So I have questions about ether itself, right? Conceptually or theoretically. So you're saying that it is a substance. It is a substance. So then it has to have mass, correct?
Yes.
And so if it has mass, why can't we detect it? Or is there a way that you know of where an experimental physicist could detect it somehow? Like, have you thought that piece of it out yet? Like, this is just it feels to me a lot like dark matter, where it's like, we hypothesize that it's there, but we can't really sort of find it experimentally.
Yes, and detecting it is very difficult. I have written some on speculations on what we might be able to do, but detecting it will be difficult. And also there's two masses. There's the gravitational mass, and then there's going to be an inertial mass. And it's worked out in the masses are worked out in the paper for what you'd expect to see. So those are the things that are there. The one thing that is predicted here is exactly where the dark matter is. So that's the new prediction that can be tested against. But as you say, it's not as direct. And what you would and unfortunately, I'm leaning to a belief. I don't know, because the size of the ethereal quanta was not. It's a free parameter in the theory, so I don't know how big it is. There were, I don't know how many constants I had put in, but then I worked them all through, and I ended up at the end there were only three, and two of them and one of them was the size. So I don't know how big it is. I think it's probably the individual ether quantum is probably subnuclear, and so that's a problem as far as isolating it. I mean, in some sense, we isolate it all the time as far as the theory is concerned, because we equate ether with electric charge, and so we see it all the time. But that's not really what you're talking about. You're talking about isolating the ether. I did at one point, and still would like to. One could do a group velocity equivalent of the Michelson-Morley test. There's some possibility you'd get a non-null result. I submitted that back in about 1990 to the NSF. We got all D's and an F because everybody knew relativity was correct. So it was going to be a waste of money. But it wouldn't cost much. We've now got these femtosecond lasers. We could do that, and so that would be. But I don't know if I don't know if it would work or not, because right now I'm also assuming there's a length contraction. I'm not entirely certain that the length contraction is true either, but I think it is. We haven't really proven some of these things that we think we've proven, so that's where that's at.
Got it. That makes sense. So I think I get that piece of it. So with respect to quantum entanglement, this is the other piece that the question that bubbled up when you were speaking is why does the ether theory solve that problem of faster than light communication? That's not immediately obvious to me.
Oh, okay. That's because that the limit of the speed of light is baked into the relativistic handling of space and time through the Lorentz transformations. So as you approach the speed of light, if you were to approach the speed of light in an apparatus, it will continually shrink in the direction it's
Mhm.
moving until it hits a point. So you can't possibly get anything physically past it. But in an ethereal standpoint, what's happening there instead is that the physical length of the device, whether it be a rocket ship or the Michelson-Morley mirrors, they're shrinking, not space itself. So you no longer have a limit based upon space and time inherently. You have a limitation on the measuring sticks and the clocks. So that those are physical entities. If the quantum nature of entities is, and I like the model that a quantum is a wave packet, because if you do a Fourier analysis of the wave packet, you're going to get an uncertainty principle there as well, which directly leads to Heisenberg's. So
Hmm.
I believe that's the underlying nature of things. I think we've got wave packets. You may be able to see that it collapses faster than the speed of light, because all it's doing is it's going to zero here and it's popping up there. So something wouldn't necessarily have to travel. It needs to collapse in a way that does not have to be limited by the speed of light. That's am I clear? Maybe
It,
I'm not, because
well,
maybe
well,
I don't.
as much as you can be with somebody who has limited, as
Well,
limited physics background as I have. I think I get it.
okay.
Um, so I wanted to pivot to another topic because I noticed that in your bio it says you're a Christian as well, and this is a topic for me that is, something I am exploring fairly deeply. I'm probably way more skilled in philosophy, particularly philosophy of religion, than I am in physics. And so when I see somebody who's a physicist, and there's a few out there that are theists, I don't care what tradition they come from. I always like to ask questions, right? Because you folks are the ones that are poking and prodding the most at the nature of reality, right? And so we can do our lay philosophy without an understanding of how the universe actually works. And we can hypothesize all these things and come up with all of these grand ideas about philosophical ideas, but I like to see that marriage between somebody who's really rigorous in looking at the math and looking at the physics of how the universe actually is to the best of our knowledge, and then somebody who came to the conclusion that there is, some God exists, or there's some underpinning religious philosophy at work. And I'm just curious to understand, like, were you like a theist before you became a physicist, or did you become a theist because of physics? That's always an interesting question to me.
I've been a theist my entire life.
Got it. Got it.
Yes.
And so question is, this is a really important question. Did working in physics challenge your existing faith, or did it reinforce it, or is it a mixed bag? Sometimes, a little bit of one, a little bit of the other.
It's been both. Yes, because the arguments that were put forth. I mean, I didn't necessarily think relativity was wrong from the get-go. And relativity, beyond being point-like, is also determinate. And so the argument that if physics is determinate, then everything must be, that leads you to Spinoza's God, which is what Einstein embraced. And so that was troubling for a
Real,
theist.
real, real quick, just because I know some of my listeners won't know what Spinoza's God is. This is sort of like the deists, right? So essentially a God that sort of set the universe in motion and just is hands off, just started the initial domino and then kind of backed off, right? Like that's kind of how you conceptualize it.
Well, mine was just I see the quote from Einstein all the time, and everything I've seen from Spinoza's God. I haven't read Spinoza, but I've seen it referred to often enough that God is essentially nature, and basically from there you're hands off. I don't know if if Spinoza got into the origins or not. I just don't know.
Yeah, but as contrasting with theism, it's not like some personal God that is, in
Right.
communication with people and, created this and, is changing reality to benefit his creation and all this traditional, most monotheistic religions are kind of like a theistic in origin. So I just wanted to draw a distinction between those two.
Okay. Yep.
Cool. So with that, groundwork laid, what about well actually let's talk generally, like why do you believe that there is such thing as a theistic god?
Well, prior to touching that, we probably should hit the soul
Okay.
because I think it's the same thing. I think when you get to the essence of existence, most or it's frequent that the present atheistic community not only do they deny God, they also deny the soul. And they do rest, from what I've seen, there's a big debate about what consciousness is. But the,
Just a little bit.
but that debate doesn't usually touch a an eternal soul that continues to exist after we've departed this world. And the idea is that it's just that we've got neurological matter in our brains, and we can sort of think, and then, well, what is this thing we think that we exist? And that ties back into the present AI debates, whether or not we can make consciousness out of silicon and all of those things. And so there's presently a strong belief in many circles of the scientific community that the soul doesn't exist. And I did an experiment on my kids when they were very young. I There's a thing called a spinner. A spinner is something that has a spin up or a spin down. And I took a beam, I thermalized a beam of spinners, and I directed them at my young sons. And I got results that were pretty definitive that they were capable of making a choice. The spinners was a box of pennies, and I told them to turn them to heads up. And my middle son said, "Can I do tails?" I said, "Yeah, that's fine too." And I gave him 100 of them each, and they all were lined up at the end. And what we do as physicists is that's what we do. We take beams and we shine them on each other, and then we see kind of what energies come out and what the results are. And in this case, if you've got 100 things that have a 50-50 chance, and you do the math, it's pretty definitive that there's something going on there. But the something that goes on there can be even more extensive, because if you look at a book, every time a letter is pressed, there's probably 100 different characters that could have been pressed instead of that letter. And if we throw out typos, which do happen, the odds of the book being written is so astronomical that there's just no way that this is done by chance. So then you've got to have the question of free will. So that's been debated for a long time, whether or not a free will exists. But that brings us back to relativity being determinate and quantum mechanics not. Because we've got evidence in the physical world that quantum mechanics is non-determinate. There's a probability that something's going to happen, but we don't know what it is. So then the question is, well, is there something within us more than the materials known to science that only interacts to make a choice of where those pennies are going to be aligned or which key I type on the keyboard? And the evidence to me is overwhelming. In fact, when I talk to people who aren't trained, of course, they think I'm an idiot for even bringing it up, because of course we have free will. This only gets when you think about things too much and you insist on having the original physicist view that you want it to be F equals ma and not equals F equals ma plus maybe some fuzz. But reality has the fuzz. And that's the root of it, I think. Right there is, do we believe that reality is determinate or not? And I would say no. And then if it's not, is there some separate substance? Now, it went for a long time. Descartes, I believe, had the dualistic view that mind was one sort of thing and matter was another. And this brings that back. There was an argument that things had to be a material in order to exist. I think that's good. Well, there may be another material that we aren't able to uh, see in any other way other than this tremendous amount of evidence that we have free will. So
Well,
that
hold on
then,
one second. I don't want to be pedantic, but I definitely want to ask the question because oftentimes, if we talk, we can end up talking past each other if we don't properly lay out our definitions. And
okay,
so, when you speak about free will, are you talking about in the literature what's called libertarian free will, or are you talking about something different?
I'm talking about the ability to make a choice.
Got it. So that's almost like Dan Dennett's quote. Like it's kind of like free won't, right? Like you have this sort of decision making ability, but there is something deterministic about making a choice. I think that there's nobody I think who's rigorous that's going to say there's no element of determinism involved in making choice, right? We have our biology, or you could even do a thought experiment. Be like, well, what thought am I going to be thinking in 30 minutes? Like, I don't know, stuff sort of just bobbles up from consciousness. And also another thought experiment is you can't force yourself to believe something, right? If you technically had libertarian free will, you could choose to believe that the sky is green, but we don't have that ability to do it. So I think there is some element of determinism involved, but I agree. I don't think that strict determinism is correct. We have the ability to choose for sure, but I think there's certain biological mechanisms. We have our evolutionary history that's baked into it. There's a bunch of deterministic machinery that's going on under the surface, but ultimately we still have the ability to evaluate something, apply reason, apply logic, whatever it is, and make an actual choice. There is an indeterminacy in how we decide things. I believe that fully. So tell me if you have a different view on that.
Well, the different view is just if you boil it all the way down to an individual quantum event. Because see, if every individual quantum event is determinate, which was the old determinate theories, then all of the things where you do make what you think are decisions really aren't, because it all stems from. It's just that the number gets so large that you can't. It becomes not visible to you, but you may still be a determinate being. And that's kind of, I think, the root of the problem is when you go all the way down to a single quantum event, is that determinate or not? Because if that's not, then everything you said is correct, as well as the bounds you just put on it. Because I haven't studied like enough philosophy, but I've been mostly focused on that which applies to what really exists at the physics level of the very small at that level. But that's how I've seen that argument go. It's at the very very bottom. If it's fully determinate there, everything is. So that was it.
Right. That totally makes sense. And ultimately, I don't have an answer that I believe super strongly in. I think it's one of those things like consciousness that's super spooky, and I'm not holding on very tightly to my conclusion. I'm still trying to explore. I'm still trying to figure this out. Have you seen Roger Penrose's work on consciousness?
I say a little, not
Like
enough.
the Yeah, I mean, this seems like a very interesting idea, the sort of microtubule argument and sort of invoking quantum mechanics in consciousness itself, and potentially the idea that consciousness itself may be fundamental in the universe. Like, do you have a view on any of that stuff, or is that totally outside of your wheelhouse?
No, I have a view, but it's fairly new, and since it's new, it could easily be wrong, and maybe you can even poke holes in it. So my view was that this second uh, material that we don't know about lives within us, and that that material is the essence of who we are, that soul. And the soul then is what we also view as consciousness. I myself have had an out of body experience when I was very, very young.
Mm.
This likely plays a role in that. Those who have had them, like me, you swear you were outside of your body. And it's pretty common. And so if that was true, and not the hallucination that is the excuse given, then that may well interact with your neurological matter, which would be in a non-determinate quantum state, and then that soul can through your neurological system execute your choices by choosing which quantum result you want it to do. So that's my theory. And it's fairly simple. So go ahead and fire away.
No. It's an interesting question, and my brain went 7 different directions. So let me start at the beginning. So you had an out of body experience, and there's a lot of literature, not a lot of literature. There's emerging literature, and I think there's a decent body to pull out some important information, right? So the near death experiences, out of body experiences. That literature exists, and I like to look at Dr. Rick Strassman's work with DMT. Are you familiar with that at all?
Not at all. No.
So he's got a very interesting hypothesis. So Dr. Rick Strassman was he's a University of New Mexico, and he was one of the people that after the Nixon prohibition on psychedelic research, he got one of the first NSF grants to perform the experiments. And he used DMT for various regulatory reasons. And he found out that every single one of his patients had the exact same story when they were injected with DMT, which was they got immediately rocketed out of their body, and they went through a fractal tunnel of light, and it was just completely overwhelming and chaotic. And then they popped into an alternate dimension, and they met entities that were conscious and interacting with them. They were speaking to them in a language that it wasn't English, but you completely understood it.
Wow.
Everybody to a person said that this realm was both the most real place they've ever been. It's hyper realistic, and everybody had an overwhelming sense of deja vu, that this is actually where they came from, right? And oftentimes people end up in this room that they sort of recognize as their subjective report would be, they recognize this is the place where your soul comes from.
Wow.
And there's this, a bunch of hypotheses around the pineal gland in the brain actually being the source of releasing endogenous DMT that could potentially mediate a sort of endogenous psychedelic experience. And people think that potentially with a near-death experience, because the reports are so similar, right? There's so many people with NDEs that give the same report as somebody on DMT. The thought is, or hypothesis is, that is actually causing, so like DMT is sort of fundamental to this concept of a soul, or, it's very nebulous, and it's, it needs more research. But I really wanted to get your take on that, because you had a near-death experience or an out-of-body experience or whatever it is. Like, what do you think about all that stuff?
Well, that's very interesting. That's the first time that I've heard about that test, and so I'll have to think about it for a while before I make a reasonably cogent answer to it. But thanks for sharing it, because that's an interesting story. I mean, when I went through it, it was very real, but apparently it was for everybody else too. And that doesn't even necessarily mean that it's not real. That's the other aspect to this, because you're getting into things like I mentioned to you on when we set this up. Some of these things are kind of in the fuzzy zone. It's not as concrete as doing some equations to derive Maxwell's equations. It's another field.
But to me that's fun. That's where the fun is.
No, it's great.
It's all on the fuzzy edges. So it's really great to watch that. I'm going to continue to pay attention to the research. I know that Robin Carhart Harris, who is based out of Imperial College London, is doing a bunch of research on slow drip DMT, because it's very short acting. So you typically, it only lasts 15 or 20 minutes, and then you're back in your body and you're very confused, and you don't know what to do. And so they've been doing longer DMT trips, because one of the problems is that it is so chaotic and it is so overwhelming, and this experience is just too much for people, and they can't even get their bearings before they have to come back to their body. And so they're looking at doing extended DMT trips to try to explore this realm and try to bring back more information. So I'm going to keep my eye on Imperial College London. They got some really cool trials around that. And if you haven't read Rick Strassman's book, it's called DMT, the Spirit Molecule. It's a fantastic read. If you're interested in these eternal questions, do we have a soul? What's the ultimate nature of reality? Man, that is a thought-provoking book. I would definitely recommend it.
All right. Took a note. Thanks. Sounds
cool.
great.
Well, hey, yeah, we're about at time. We covered a ton of ground, man, and I'm super interested to dive deeper into your work. You've certainly provoked a lot of questions in me, and ultimately, I'm just not that great at physics, and so I'm going to have to lumber along and sort of plod through it and see if I can come up with something. But the concept of ether is a really cool idea, and I really enjoyed kind of coming up to speed with some of your work, even if it's only this deep, man. So thanks for joining me. I really appreciate it. If you want to tell people where they can find you online, I really want to get some eyeballs on your work.
Oh, well, thank you very much for having me on today. The Twitter handle is Larson Delbert, and that's where I'm online. And then my works are on larsonism.com if they want to look at the published works or the webinars that are associated with it. Thanks again.
Fantastic. Thanks for stopping by. I really appreciate it.